The urinary system. The urinary system, which forms part of the excretory system, is the system responsible for removing waste products from the human body, products of cellular catabolism, in liquid form, urine. It thus ensures the purification of the blood and the maintenance of homeostasis, the body's state of equilibrium, within the body. It also maintains the blood's balance l'équilibre sanguine, i.e. the volume and chemical composition of the blood. Among other things, it removes excess amounts of certain minerals, known as electrolytes, and returns substances that are essential for the body to function properly to the bloodstream. Every day, a person produces between 800 and 2,000 milliliters of urine. This system consists of a series of organs that we will examine: the 2 kidneys, the 2 ureters, the bladder and the urethra. Traditionally, the urinary system is divided into 2 functional units. Lower part of the device, it is a single, central structure formed by the bladder and the urethra. It is responsible for storing and excreting urine. It differs between men and women. Upper urinary tract. It is bilateral and symmetrical, formed by the 2 kidneys and the 2 ureters. It is the same in men and women. It is responsible for the formation of urine and its transport to the lower urinary tract. External configuration of the kidney. The kidneys are flat, oval-shaped organs, often described as bean-shaped. The outer surface is convex, the inner surface is concave. The hilum is located on the inner surface of the kidney. It is the opening into the organ through which all the nerves, lymphatic vessels, blood vessels, etc. pass. The surface of the kidneys is smooth and reddish-brown in color. On average, they are 12 centimeters high, 6 centimeters wide, 3 centimeters thick, about the size of a fist, and weigh between 110 g and 160 g. These measurements vary greatly from one person to another. They are usually located between T12 and L3, right kidney. In most people, the left kidney is higher up than the right kidney. The kidney is surrounded by a fibrous capsule. It consists of the renal parenchyma, outer layer, and the renal sinus, inner layer. The renal parenchyma consists of 2 zones: the cortical zone, cortex, and the medullary zone, medulla. The renal sinus consists of the calyxes, the bassinet, the ureter. The renal parenchyma. The renal parenchyma consists of 1. The medullary zone. It is dark red and contains A. The renal pyramids, Malpighi's pyramids. There are between 8 and 10 of these per kidney, and they are separated from one another by the renal columns. Each pyramid has an internal apex that protrudes without the sinus and an external base. The tips of Malpighi's pyramids form the taste buds. B. Bone marrow irradiation. Ferrine pyramids originate at the base of Malpighi's pyramids and extend into the cortical area. 2. The cortical zone. It is reddish-yellow in color and surrounds the renal pyramids. It contains A. The labyrinth, the region extending between the medullary radiations. B. Batan's columns, renal columns, the region between the pyramids of Malpighi. The renal sinus. The renal sinus comprises 1. Small and large calyxes. The small calyxes, the place where urine from the papillae flows into large calyxes, a cluster of 2 to 3 small calyxes. 2. The bassinet. It results from the union of the large chalices. It plays a contractile role that allows urine to flow downwards. 3. The ureters. They follow on from the basin's sweet auxiliary bassinets and measure approximately 25 centimeters in the abdominal region, and are 3T. They carry urine from the renal pelvis to the bladder through peristaltic movements. The bladder. It is a hollow organ, defined as a muscular membranous reservoir that stores urine between urinations. This depends on the amount of urine. When it is empty, it is in pelvic position, with an anteroposterior diameter of 5 to 6 cm and a transverse diameter of 7 cm. When it is full, it is in the abdominal pelvic position, with an anteroposterior diameter of 6 to 10 cm and a transverse diameter of 8 to 10 cm. Its physiological capacity is to 250 to 500 milliliters. Its maximum capacity is 2 to 3 liters. Maximum estate to 2 or 3 liters. The urinary tract. It is a muscular membranous duct that excretes urine. In men, it has a dual function, urinary and genital, as a passage for sperm. In men, the urethra begins at the neck of the bladder and ends at the tip of the penis at the urethral opening. It is approximately 16 centimeters long on average. It passes through the prostate and the perineum and enters the corpus spongiosum. The male urethra consists of two segments. The prostatic urethra runs vertically through the prostate. The membranous urethra. In women, it begins at the bladder neck and ends at the vulva at the urethral opening. It measures on average 3 centimeters. Renal physiology. Blood purification function. The kidney's primary and essential role is to filter the blood. The kidney receives a quarter, 1/4, or a fifth, 1/5, of the cardiac output, CO. It receives this high percentage because one of its functions is to filter the blood. In other words, it receives a large volume of blood so that it can be filtered. This means that the kidney needs blood for two reasons. Since it is an organ, it first needs a supply of energy, oxygen and glucose. It needs a blood supply and vascularization. For purifying the blood, which is its primary function. How will the kidney carry out this filtration? First, it extracts, removes, the substances or nutrients that the body needs from this blood. For example, glucose. When glucose passes through the kidneys reabsorb 100% of it. There is no glucose in the urine, except in people with diabetes, as these are substances the body needs. Proteins. There are no proteins in urine, as these are substances that the body needs. In other words, in a healthy person, the kidneys will reabsorb nutrients for the body, as these are substances the body needs. B. On the contrary, it will secrete, or excrete the excess substances, or waste products. Waste is generally either exogenous, medicines in particular, antibiotics, particularly beta-lactams such as penicillin, amoxicillin, etc. Oral vitamins, e.g. vitamin C, donate these items. B. Contrast agents. These are products that can be taken, but only under specific circumstances. For example, radiological examinations, particularly CT scans, for certain organs. A CT scan involving the injection of a contrast agent is usually requested. These agents are excreted by the kidneys. That's why, when we ask for a scan, we always ask for a kidney function test as well. In other words, we always need to check kidney function to see if it's working properly before administering these drugs. 2. Endogenous, such as uric acid, urea, creatinine metabolites, protein breakdown products, H+ ions. Why are there excess H+ ions? Since people tend to eat foods that are generally high in protein, so there is always a tendency for there to be an excess of H+ ions. And H+ ions determine the pH. So, due to our diet, the body always tends towards acidosis, acidity, because H+ ions are constantly being produced, and it is the kidneys that eliminate the excess H+ from the body and play a role in maintaining pH. That is why the pH of urine is lower, more acidic, than that of blood plasma. The kidneys also play a very important role in maintaining this balance by eliminating excess hydrogen ions. NB, note, some substances are excreted by the kidneys and others by the liver. For example, paracetamol is eliminated by the liver. In other words, if there is an overdose of paracetamol, there is a risk of liver toxicity, which may damage the liver. The role of purification is vital. In other words, if the excess hydrogen is not eliminated, over time this will lead to metabolic acidosis. And if there is acidosis, a drop in pH, clinical complications will arise, and it may even lead to what is known as acidosis-induced coma, which ultimately results in death. As pH is a very important parameter, it must remain within a well-defined range, as this is the appropriate pH for various enzymatic reactions. To perform this function, purification, you need at least one kidney to perform this filtering function. If a patient is missing both kidneys, or has kidney damage, this filtration must be carried out immediately, otherwise, the patient will die. You need to undergo what is known as dialysis. Dialysis is an extrarenal, extracorporeal, purification process. In other words, it involves purifying the blood using an extracorporeal device. We offer hemodialysis and peritoneal dialysis. Hemodialysis, this is the most commonly used method. The blood will be drawn, passed through a machine that will filter it, and then returned to the arm. B. Peritoneal dialysis enables people to undergo dialysis at home, meaning they do not have to travel to a dialysis center. Occurs between the two layers of the peritoneum. There is an exchange between these two layers. A solution is introduced. As it passes between the two layers, an exchange takes place and waste products are removed. Blood purification function. It is in the kidneys that either the excretion of excess food or its reabsorption if necessary. Examples of foods that the kidneys help to excrete. 4. Sodium. If someone follows a low-sodium diet, the kidneys will retain as much sodium as possible for the body. However, if they consume a diet very high in sodium, the kidneys will eliminate the excess, excrete it. And this will be used in A. Regulation of osmolarity. Osmolarity, concentration of a solution expressed as the number of particles per liter, is a very important parameter that must be maintained within a well-defined range, 280 to 300 osmol per liter in blood plasma. If there is an increase or a decrease, that is a problem. Osmolarity equals twice the serum sodium concentration. In other words, serum sodium concentration is a parameter that determines osmolarity. This means that by regulating serum sodium levels, we will achieve normal osmolarity. B. Blood pressure regulation. Blood pressure is also a very important factor and must be kept within a specific range. If our osmolarity is normal, our blood pressure is normal, since osmolarity is a factor that influences blood pressure. These two factors are part of homeostasis, the body's internal balance. When our bodies are functioning properly, our homeostasis is maintained and regulated. Homeostasis is a set of factors or parameters that ensures the body functions properly: blood pH, osmolarity, blood pressure, and even body temperature. The kidneys play a role in keeping all these parameters within a specific range, i.e., in maintaining the body's homeostasis. B. 4. Potassium. There are several foods that are rich in potassium, such as potatoes, dates, bananas. In a healthy person, the kidneys eliminate the excess. In a patient with kidney failure, there is a risk of hyperkalemia, which can lead to cardiac arrest and, consequently, death. That's why, when the kidneys stop working, you have to act quickly and filter the blood, or by emergency hemodialysis in the event of acute kidney failure. Or gradually, in the case of chronic kidney disease, which develops gradually. Or a kidney transplant, if one is available, otherwise, the person will die. Endocrine function. Production of erythropoietin, EPO, erythropoiesis. It is a glycoprotein hormone that stimulates the maturation of red blood cells. In adults, it is secreted by the kidneys, in the fetus, by the liver. People with chronic kidney disease do not produce erythropoietin, their kidneys do not function as endocrine organs, even when undergoing hemodialysis. Consequently, red blood cells do not mature, and the person will develop what is known as anemia. B. The production of vitamin D. Generally speaking, we have 7-dehydrocholesterol as a lipid in our diet. And thanks to the sun's UV, ultraviolet, rays, this 7-dehydrocholesterol is converted into cholecalciferol, which is vitamin D3, a form of vitamin D that is still inactive. That is why it is recommended that children and the elderly spend a short time, 10 to 15 minutes, in the sun to trigger that initial reaction, which is essential for the formation of vitamin D3, and, consequently, for the subsequent reactions that enable bone calcification and strengthening. This vitamin D3 undergoes a further reaction, hydroxylation, in the liver, producing 25-hydroxycholecalciferol, but this is still inactive. It undergoes a third reaction, hydroxylation, in the kidneys to produce 1,25-dihydroxycholecalciferol, which is the active form of vitamin D, calcitriol. It is this active form that enables our body to bind Ca2+ to the bone, thereby making the bone strong. This is known as bone mineralization, or calcification. People with kidney failure do not undergo this second hydroxylation, so they do not have active vitamin D. As a result, these individuals develop osteoporosis, a condition known as bone decalcification. Renal blood supply. The kidney is a highly vascularized organ, 1/5 of cardiac output, or 1,200 milliliters per minute. The renal circulation is characterized by the complex anatomical distribution of blood within the kidney. Serves a dual purpose: maintaining homeostasis of body compositio. Nutritious supply kidney cells with the nutrients they need for their metabolic activity. Each kidney receives a renal artery from the aorta. Each renal artery gives rise to the interlobar arteries interlobars et au system of arcuate arteries. From the latter branch off, the ascena artery system the interlobular arteries, qui donnent naissance auxiliary arterioles afferentes des glomerules, qui donnent alors naissance au réseau capillaire peri-tubulaire. The true right arteries run deep into the medulla. The veins follow roughly the same course as the arteries. They leave the hilum and drain into the vena cava. The distribution of this vascularization is very uneven, rich and dense cortical blood supply. The spinal cord has a poor blood supply, supplied by the right arterial system, approximately 20%. Like every other organ, the kidney has its own functional unit called nephron, whose role is to filter the blood. Each kidney contains around 1 million nephrons. The nephron can be divided into two parts: a vascular portion and a tubular portion. The renal artery is about to undergo a series of divisions. When we reach the nephron, we arrive via an arteriole, a small artery. As this is an arteriole that carries blood away, it is called afferent arteriole. This vessel carries blood to the microscopic filtration zone known as the Malpighi corpuscle. The glomerulus is a cluster of porous blood capillaries through which fluid is filtered, much like a sieve. Much of the plasma and the blood components that are too large to pass through the pores, red blood cells, platelets, white blood cells, most proteins, etc., then continue on their way. Once the blood leaves the Malpighian corpuscle, it continues its journey via the efferent arteriole. The blood then passes through another set of capillaries, the peritubular capillaries, which reabsorb most of the fluid filtered in the glomerulus. Finally, the blood leaves the nephron via the interlobular veins. The tubular part of the nephron. This is the second part of the nephron. It is almost in contact, not in direct contact, with the vascular tissue. In the first part of the tubule, we find what is known as the Bowman's capsule, which contains the capillary network, the site of exchange between the vascular and tubular parts of the nephron. Subsequently, we will have proximal convoluted tubules, followed by a loop that extends all the way to the medulla. This is Henle's loop. After this bend, we will have the distal curved tube. The distal convoluted tubule continues into the collecting duct, which may join several nephrons. The function of the nephron. The functioning of the nephron can be divided into three phases: glomerular filtration, tubular reabsorption, tubular secretion. Glomerular filtration. Glomerular filtration is the fundamental stage in the formation of urine. I don't know what this is. The volume of fluid filtered in the glomeruli, 180 liters per 24 hours for a body surface area of 1.73 square meters, is significantly reduced as it passes through the tubules. Diuresis is only 1.5 liters per 24 hours, therefore, 99% of the water is reabsorbed. This leads to the formation of the primitive urine. Elle lieu dans le corpuscule de Malpighi. Glomerular filtration is a special case of capillary exchange, as the transfer is unidirectional, filtration without reabsorption due to the exceptionally high value of Pc. Reabsorption refers to the passage of a substance from the filtrate into the peritubular capillary. The filtrate entering the proximal convoluted tubule, PCT, is rich in beneficial substances, water, glucose, amino acids, salts, etc. These substances must therefore be reabsorbed and returned to the bloodstream. In the end, we will have a total urine output of approximately 1.8 liters. 99% of the filtrate will be reabsorbed. Tubular cells carry out this reabsorption through complex processes, passive transport, active transport, etc. Reabsorption. Most of the reabsorption takes place in the TCP. It also occurs in the distal tubular segments, where reabsorption is regulated and is subject to hormonal influence. Secretion refers to the passage of a substance from the peritubular capillaries into the tubular lumen, almost equal to the opposite of reabsorption. Metabolic waste products, urea, uric acid, creatinine, must be removed from the blood. Certain ions, H+, K+, will be excreted in the urine, acid-base and electrolyte balance. Certain medicines and toxic substances are not filtered out and will be excreted in the filtrate to be eliminated from the body. Hormonal regulation of tubular processes. The reabsorption of water and salts by the renal tubules is subject to hormonal regulation. These processes help regulate blood volume and, consequently, blood pressure. The main hormones involved are renin, aldosterone, antidiuretic hormone, ADH.